Hello, my name is Kathleen and I'm a third-year PhD candidate in the Department of Chemistry at Northwestern University. I am currently a member of Professor Chad Merkin's lab, and I'm originally from Southern New Jersey, which is where I did my undergraduate studies. There I went to Stockton University, where I double majored in biochemistry, molecular biology, and chemistry. Nanoscale materials are defined as having at least one dimension between 1 and 100 nanometers. A common theme in nanoscience and technology research involves learning how a nanomaterial structure will impact its function. And this concept of structure impacting function is important across scientific disciplines and across length scales, but it is particularly critical at the nanoscale. A fascinating aspect of working at this length scale is that miniaturized versions of objects have different properties than those of their larger counterparts, such as gold, for example. Modern nanochemists are programming nanoparticle assembly and constructing new materials block by block. And by understanding the chemical design rules that govern structural outcomes, researchers are learning how one can deliberately tune the properties and functions of resulting materials. As mentioned by Max and Katie in the earlier videos of this series, the Merkin lab utilizes programmable atom equivalents, or PAEs, as building blocks for larger nanoparticle crystals. PAEs are nanoparticles that are functionalized with dense, radially oriented DNA strands on their surfaces. We think about the nanoparticle core as being analogous to an atom, and the DNA being analogous to the bonding element, or unpaired electrons. In the familiar Lewis dot structures that we study in general chemistry, the nanoparticle would be the central element, and the DNA would be the valence electrons. But keep in mind that instead of talking about electronic interactions through electron pairing between atoms in conventional chemistry, we are talking about DNA pairing or hybridization interactions between PAEs in modern nanochemistry. And unlike with traditional atoms, whose numbers and bonding are limited by nature, PAE bonding allows for nearly infinite number of core and building block motif combinations. But PAEs, no matter their composition, all crystallize according to the same set of design rules. So, what are those design rules? The design rules are based upon the complementary contact model, or CCM for short, which Katie introduced in the previous video. The design rules apply the CCM for specific systems of PAEs under a certain set of experimental conditions. The first design rule is that PAEs in a system will organize themselves to maximize pairing interactions or DNA bond formation. This will result in the most thermodynamically favored structure. So let's look at simple examples of this design rule in action. Imagine a system consists of one type of spherical PAE, all the same size and all modified with the same type and number of self-complementary DNA, an AA system. In this case, the PAEs bind to those that are like themselves, and we observe the assembly of a face-centered cubic, or FCC crystal lattice, because this arrangement maximizes the number of DNA linkages between particles of this type. Now let's consider a slightly more complex system, an AB system. Here, the two spherical PAEs are still the same size, but although A and B are surface modified with the same number of DNA strands, the strands are no longer identical, but instead are complementary. The two PAEs in this system can therefore form AB interactions, but not AA and not BB interactions. In this case, the thermodynamic product is a body-centered cubic, or BCC crystal lattice. This lattice forms because it maximizes the DNA connections between these types of particles. But not all systems are that simple. What happens when all the nanoparticles are not the same size? What if all the DNA strands are not the same length? Are there other design rules at play? We can use this AB system to illustrate another key design rule. The overall size of the PAEs, rather than the sizes of their individual nanoparticle or DNA components, dictates its assembly and packing behavior. In other words, if the overall size of the PAE, meaning total size of nanoparticle core plus the DNA shell, are the same, then these particles will always assemble in the same way. For example, We see that in our A-B system, for PAEs with the same overall size but different nanoparticle core sizes and DNA lengths, a cesium chloride lattice results, which exhibits the same PAE arrangement and connectivity as a BCC lattice. But the cesium chloride lattice is a form of BCC lattice where the atoms, here the nanoparticles, are not the same size. Another type of complex system involves PAEs that are different sizes and ones that have different numbers of DNA strands on their surfaces. In such a binary system, researchers have delineated another design rule that states the size ratio, defined as the ratio of PAE sizes, and the DNA linker ratio, defined as the ratio of the number of DNA bonding elements on each of the two PAEs, dictate the thermodynamically favored crystal structure. And that is because these parameters are important for dictating the stability of the resulting crystal. The size ratio impacts particle packing, and the linker ratio affects DNA bond formation. In general chemistry, we use phase diagrams to illustrate how a molecular species will exist in either the solid, liquid, or gas phase, depending on temperature and pressure conditions. And phase diagrams are also used to describe alloys, such as steel, that can be made up of different ratios of iron and carbon. Similarly, with PAEs, we have built phase diagrams relating this DNA linker ratio and size ratio to understand and predict which structures will form for particular PAE starting materials. And these phase diagrams offer a lot of predictive power. Colloidal crystal structures, analogous to those that are typically introduced in general chemistry, and others have been obtained as a result of these phase diagrams. And it doesn't end there. PAEs differ from atoms in that the particle, or the atom, and the DNA bonds can be tuned independently to create unique multi-component systems. And this capability follows from another interesting design rule that states two systems where the PAEs have the same size ratio and DNA linker ratio exhibit the same thermodynamic product. For example, these systems where the PAEs have the same overall size ratio and DNA linker ratio, but are composed of different types of cores and nucleic acids of different sizes and lengths, all assemble into cesium chloride lattices with different lattice parameters. The core compositions do not matter. Over the past decade, researchers have used principles that follow from the CCM to develop a wide variety of other design rules to create more complex crystal lattices. To date, researchers have prepared thousands of crystal lattices that span over 90 different crystal symmetries, including S quasicrystals, as well as lattices not found in nature. And what this means is that since we can control structure, and because structure and function are linked, we can therefore tune function to create new materials with interesting optical, mechanical, or biological properties. For example, the Merkin lab has demonstrated that we can tune the way colloidal crystals interact with light by changing the diameter of gold nanoparticles, or the crystal lattice constants. This holds tremendous promise for controlling the optical properties of colloidal crystals based on semiconductor nanoparticles called quantum dots. We have also prepared nanoparticle crystals with unusual shape memory properties. The DNA bonds allow these crystals to bounce back from deformations that would lead to irreversible damage with other types of crystals. These crystals could find use in sensing, robotics, and energy storage. Now, I got involved in research as a college freshman because I wanted to apply what I learned in my general chemistry classes to the real world. My undergrad research experience significantly influenced my decision to pursue my PhD, and I learned many valuable lessons that I carry with me to this day. And one of the biggest reasons I came to graduate school at Northwestern was for the opportunity to fully immerse myself in world-class research. I love applying what I learned in the classroom and in my reading to solve problems. And what I found much more rewarding than simply learning how to perform experiments is how to think like a scientist. I've learned how to critically analyze a question and come up with my own answers that can shift paradigms. For pursuing any career in the STEM field, gaining research experience is critical, and it is important that you start early, even if it seems overwhelming. Many people will be willing to help you along the way. And if you're also interested by the possibility of applying what you learn in general chemistry to more modern research areas, I encourage you to definitely get involved. Thank you.